Hey everyone, welcome to this explainer. Today we are doing something really cool. We're literally stripping back the layers of reality. We're going to embark on a fascinating journey to discover what the universe is fundamentally made of and look at the very fabric of our surroundings. So let's dive right into it.
Think about this for a second. What do a massive burning star, a random pebble you'd kick on the street, and a tiny drop of water actually have in common? I mean, on the surface, they couldn't seem more different, right? But what if I told you there's a hidden, unifying connection tying all of these things together, along with the air you breathe and the food you eat? It's the one connection that completely defines the physical world around us.
To uncover that connection, here is the roadmap for our explainer today. We'll start with what exactly is matter, then the secret life of particles, next the three states of matter, followed by how matter changes state, and finally we'll wrap up with the magic of evaporation. Let's get started. All right, Section 1. What exactly is matter? The foundation of everything. You know, since the dawn of time, humans have had this deep obsession with understanding and categorizing their surroundings. Ancient Indian philosophers beautifully classified everything into 5 basic elements, the Panch Tatva, which were earth, air, fire, sky, and water. The ancient Greeks were actually on a very similar wavelength. But modern science, it's a bit more precise. Today we define matter as anything that occupies space and has mass and volume. For this explainer, we're going to focus strictly on those physical properties. Moving right along to Section 2, the secret life of particles, visualizing the invisible. So for the longest time, there was this massive debate. Is matter one continuous block, like a plank of wood, or is it made of tiny individual pieces, kind of like sand on a beach? Well, to figure this out, we have to mentally zoom way in. Matter is definitely not a continuous block. To prove just how infinitesimally small these building blocks are, let's walk through a classic chemistry experiment. Imagine taking just 2 or 3 tiny crystals of potassium permanganate, which is this incredibly vibrant, deep purple stuff, and dissolving them in 100 milliliters of water. Then you take just 10 milliliters of that purple water and mix it into 90 milliliters of clear water. Take 10 ml of that new mix and put it in another 90 ml of clear water. You repeat this dilution 5 to 8 times.
And here is the absolutely mind-blowing part. With every single dilution, sure, the color gets lighter, but the water is still visibly purple. It is absolutely amazing when you do the math here. Just a few crystals can color a massive volume of water, up to 1,000 liters. That means a single tiny crystal has to contain millions upon millions of tiny particles that just keep dividing themselves into smaller and smaller pieces. We are talking about a scale that's almost impossible to wrap your head around.
Okay, so these invisible particles, they actually follow some pretty strict rules. First, they have space between them. When you dissolve salt in water, those salt particles literally slip into the empty gaps between the water particles. Second, they are continuously moving because they have kinetic energy. Think about it. When someone is cooking sizzling hot food in the kitchen, you can smell it from 3 rooms away almost instantly, right? That's because the food's aroma particles are literally zooming through the air to reach you. And third, they attract each other. There is a hidden force acting between them, keeping them together, though the strength of that force really varies.
Which brings us to Section 3, the 3 states of matter, solids, liquids, and gases.
Let's zoom back out. How do those 3 microscopic rules create the physical world we actually interact with? Well, they give us our distinct states of matter. Let's contrast the 2 extremes, solids versus gases. In a solid, like a block of wood or your phone, the particles are super attracted to each other. They're packed incredibly tight with almost no space, making them rigid with a fixed volume. You can't just wave your hand through a solid block of wood. You need a black belt in karate for that. But a gas? Totally different story. Gas particles are moving at high speeds in random directions, with barely any attraction to each other. They just expand to fill whatever container they're in, and because of all that empty space, they are highly compressible. Which perfectly sets up this really cool everyday question. Have you ever wondered how a balloon seller at a park fills dozens and dozens of massive balloons from one relatively small cylinder? It's all about that compressibility. Because of the invisible space between gas particles, you can squish a huge volume of gas into a tiny cylinder. When you let it out, it expands to fill hundreds of balloons. It's everyday physics magic.
All right, Section 4, how matter changes state, the power of heat and pressure.
We all know matter can change states, right? Ice melts into water, water boils into vapor. But how do we actually force that change to happen? It comes down to 2 powerful tools, heat and pressure. Quick detour on temperature, though. Scientists love using the Kelvin scale instead of Celsius.
To convert Celsius to Kelvin, you just need one magic number, 273. Just add 273 to your Celsius reading, and boom, you have Kelvin. It's a crucial math trick for measuring the precise energy states of these particles.
So what exactly is happening on a microscopic level when you turn up the heat? It's basically a story of increasing chaos. First, the kinetic energy of the particles shoots up. Because they have more energy, they start vibrating furiously. Eventually, the energy from the heat completely overpowers the forces of attraction pulling them together, and they literally break free from their fixed positions. That exact moment, that's when a solid melts into a liquid, or a liquid boils into a gas. It's essentially a microscopic energy jailbreak.
But wait, sometimes matter just completely skips a step. It's a fascinating process called sublimation. If you apply heat to crushed camphor, it doesn't melt into a liquid puddle first. It changes straight from a solid directly into a gas. It completely bypasses the normal rules. And by the way, if you reverse it, gas turning directly into a solid, that's called deposition. Now, temperature is only half the equation. Pressure matters just as much. By applying a ton of pressure and dropping the temperature, you can force gas particles so close together they actually turn liquid. Or think about solid carbon dioxide, which we all know is dry ice. It's stored under extremely high pressure. The second you drop that pressure down to normal, everyday atmospheric pressure, 1 atmosphere, it turns directly into a gas without ever becoming a liquid. That's exactly why dry ice gives you that awesome, spooky, liquid-free fog for special effects.
Finally, Section 5, the magic of evaporation cooling the world down.
So do you always have to physically boil a liquid to turn it into a gas? Nope, not at all. Puddles dry up, wet clothes dry in the sun. This is evaporation. It's a surface phenomenon where the particles right at the top of the liquid get just enough energy to break away into vapor, way below the boiling point. There are 4 main things that speed this up: increasing the surface area, turning up the temperature, lowering the humidity, and cranking up the wind speed. Think about doing laundry. If you want your clothes to dry fast, what do? You spread them out, that's surface area. You hope for a hot, sunny day, that's temperature, and a nice breeze blows the vapor away. You're literally hacking physics to do your chores faster. Now here's a highly relatable question for you. Have you ever put a little nail polish remover, acetone, or even just sprayed some perfume on your hand and it instantly feels super cold? Why is that happening? It's not like the bottle was sitting in the fridge. The secret lies in heat transfer. Those liquid particles need energy to evaporate. And guess where they steal it from? Your skin. They absorb what's called latent heat energy straight out of your palm to fuel their escape into the air, leaving your skin with less heat. Your brain registers that missing heat as feeling cold. It's actually a brilliant biological survival trick too. It's exactly why we sweat to cool down in the heat, and why wearing cotton in the summer feels so good. The cotton absorbs your sweat, exposes it to the air, and kicks off that evaporative cooling process. So we started by looking at the whole universe and zoomed all the way down to the tiny particles in a drop of perfume. I want to leave you with one final kind of mind-bending thought to chew on. If all the solid, rigid objects around you right now, your desk, your phone, the floor under your feet, are actually just millions of vibrating particles separated by tiny, invisible gaps, how much of your solid physical world is actually just empty space? Kind of makes you reframe your entire reality, doesn't it? Thank you so much for joining me on this explainer. Keep questioning the world around you, and I'll catch you next time.